Hey guys. So, what we got going on today is we're going to be talking about gas laws, specifically the combined gas laws and the ideal gas law. And then a little bit about what we mean when we say an ideal gas and how that differs from a real gas. Here's what sections it is in your textbook if you're interested, and which learning objectives in the AP Chemistry curriculum it meets. So, gases are the best understood phase of matter because way back when, before we had all of these fancy labs and fancy technology, they were able to figure out a lot of things about the relationship between gases through relatively simple experiments. Okay? And they all relate the temperature, the volume, and the pressure to the amount of gas, or something about that sample. So the first one discovered was the relationship between pressure and volume, and it was discovered by a guy named Boyle. So what he figured out is that the volume of a confined gas is inversely proportional to the pressure. What does that mean? AKA, as the volume decreases, the pressure increases, and vice versa, which makes sense. Remember, pressure is how much the gas particles are running into the walls of their container, so if you give them less room to move, they're gonna run into the walls more. Okay? So pressure times volume is gonna be a constant. And how you'll often see this written is as P1 V1 equals P2 V2. Okay? So if you change the pressure, it's gonna change the volume, but the product of it is gonna remain the same. So let me prove this to you guys. Okay, so right here I have a gas pressure sensor. It senses pressure. And I have a syringe. Right now the syringe is at 15 milliliters. And let me plug that in so I can get the pressure for you. I messed up. I will cut this out of the video. Okay, so the pressure right now is at 103.9 kPa, while it's at 15 milliliters. So let's go ahead and set that. It's at 15 milliliters. Okay, and now I'm going to decrease the pressure down to 10 milliliters. And you see the pressure increase. Okay, so that's at 10 milliliters. Okay, what if I decrease the pressure all the way down to 5? It's getting harder to push because of all of the pressure. It's hard to do this on one hand. Hey, give it. Okay, that was at 5 milliliters. Okay, so now let's go back and let's extend the pressure. Okay, now I'm taking it back to 20 milliliters. Okay, and now back to 25. So we can get a good complete graph. Okay, and out to 30. See if I can get it to stay. Boom. 30 milliliters. Okay, so you can see that inverse shape on the graph. At the low volumes, it was at high pressure, and at the higher volumes, it was at lower pressure, which makes sense. And I can also show you if I do a new calculated column, which I can do right somewhere. Oh, stop. Data, new calculated column. I'm going to create a new column that is going to be pressure times the volume. So volume multiplied by pressure. And you can see that these numbers, they change a little bit because obviously I wasn't being too careful, but they're all about the same, okay? They're all, you could round them up to about 1600, okay? So that is proving to us that PV is a constant, okay? Our graph looked pretty similar to this. High pressure is at low volumes, and low pressure is at high volumes, which makes sense because they're going to run into the walls more. Okay, so let's do an example of Boyle's Law. Sulfur dioxide is a gas that plays a central role in the formation of acid rain and is found in the exhaust of automobiles and power plants. Consider a 1.53 liter sample of gaseous sulfur dioxide at a pressure of 5.6 times 10 to the third pascals. If the pressure changes at a constant temperature, what will be the new volume? Okay, so remember our equation is P1 times V1 equals P2 times V2. So our initial volume was 1.53 liters, and our initial pressure was 5.6 times 10 to the third pascals. Okay, when using these gas laws, you can use any pressure unit that you want as long as you stay consistent. Same goes with volume. It doesn't matter if you're using liters or milliliters as long as you stay consistent. Okay, and then the pressure is going to change. So 1.5 times 10 to the fourth, that's going to be our P2. Okay, and it's asking for our V2. Okay, so our V2 is what we're trying to find. So now, all we got to do is plug and chug. Okay, P1, 5.6 times 10 to the third pascals times V1, 1.53 liters equals P2, 1.5 times 10 to the fourth pascals times V2, which is what I'm trying to find. Okay, in order to solve for the V2, we divide both sides by 1.5 times 10 to the fourth. Okay, that'll cancel out there. The Pascal units canceled out with the Pascal units. The units that we're left with is liters, which is cool because that's a volume. That's what we're looking for. Plug it into your calculator. Times 1.53 divided by 1.5 times 10 to the fourth, and you get 0.571 liters. And then we want to check them to make sure that makes sense. The pressure is increasing, okay? Increasing from 10 to the third to 10 to the fourth, so by almost a whole order of magnitude. So we expect the volume to decrease. That's what's making the molecules run into the walls more. And indeed, the pressure decreased. Okay, cool? Okay, cool. Let's look at another relationship. Okay. This one is Charles's law because he's the one who figured it out, and it's about the volume and the temperature of a gas if they're held under constant pressure. An easy way to think of this is to think of a balloon. Okay, balloons can expand and contract to keep their inside pressure the same as the pressure outside the room. So if you picture a balloon in an ice bath, okay, the balloon's going to shrink. Try it. Put a balloon in your freezer. Let me know how it goes. Okay, versus if you take a balloon outside into the heat, into the hot air, the balloon is going to expand. Okay, these two things are directly related. They're directly proportional. So as the temperature goes up, the volume goes up, which makes sense. If the temperature goes up, the molecules are moving around more, and if they're moving around more, they're going to try to hit the walls of their container, which is going to move those walls out, if they can. Okay? So when things are directly proportional, that means that V1 and V2 and T, my smartboard isn't working, T1 over T2. So it looks like that. V1 over T1 equals V2 over T2. That's what it looks like when things are directly proportional. Okay, you can see that in this graph as well. Okay, they did this for gases, different amounts of gases. So as the temperature goes up, you see the volume going up. Okay, and it goes up pretty consistently. I'm going to go ahead and prove this one to you as well. So to my gas pressure sensor, I am going to hook up a empty test tube. Okay, it's not empty, it is obviously filled with gas. Okay, I'm gonna hook that up to my gas pressure sensor. And then I also have a temperature probe hooked up. So you can see right now just at room temperature, okay, the room is at 25.2 degrees Celsius and the pressure is at 102. Okay, so I'm going to go ahead and keep this data point. Okay, now right here I have a thing of water that I boiled. Okay, so I'm going to put my gas particles into the boiling water so that the boiling water transfers its energy through the glass into there and heats up those gas particles. And I'm going to take the temperature of the water. Okay. Now I have to wait for a little bit to let the temperature stabilize out and also the pressure stabilize out. Okay, so that all of those gas particles heat up and get that energy and come to the same temperature as the water. Okay. So we can see here that the pressure is still increasing. Okay. Or is it not? Is it staying? Looks like it's staying pretty much around 111.93 to 0.95. Temperature is staying pretty consistent, so let's go ahead and keep that data point. Okay, now I'm going to take them both out of the hot water, move the hot water out of my way, and in my fridge I have some cold water. So here's some cold water. Okay. And I'm going to cool the molecules down. Okay. So I'm going to let them sit in there and cool down. You can see as they're cooling down, the pressure is decreasing. Okay. Before it was at 112, now it's cooling down to 102 as the temperature drops. Okay. We'll see how far down the pressure goes. Once I think it's pretty much stabilized out, we'll go ahead and keep that data point. So it's still going down. Now it's at 0.7, 0.6, 6, 7. Okay. Looks, oh, nope. Pressure is still decreasing. Now it's down to 0.5, 101.5. It takes a while for that energy to transfer. Right now what's going on is the energy from those gas molecules is transferring out to the water. If we left this here for a long time, we would actually see the temperature of the water change. But we have a small amount of gas particles compared to the amount of water that there is, so that change is going to happen a lot more slowly. Okay, now this is down to 0.42, and we'll just go ahead and keep it at that point, because I think now it's just hovering right around, nope, went down to 0.3. Okay, we'll go ahead and keep it. Okay, and now let me just auto scale this data for us so we can really see the trend. Okay, there, right there, you see that nice linear trend, okay, as it goes from the low temperatures with the low pressures up to the higher temperature and the higher pressures. Okay, it is very linear in that sense. Okay, cool? Okay, cool. So let's do a problem like this. Okay, a sample of a gas. Oh, let's write the equation first for you guys. V1 over T1 equals V2 over T2. Okay, a sample of gas at 15 degrees Celsius. So my T1 is 15 degrees Celsius. And 1 atmosphere has a volume of 2.58 liters. Okay, what volume will the gas occupy? So we're asking for the V2 at 38 degrees Celsius and 1 atmosphere. I didn't write down the 1 atmospheres because the pressure is staying constant. When it's staying constant, you don't need to worry about it. Okay, and T2, which is 38 degrees Celsius. A little note, whenever we're working with temperature though, we are going to need to work in Kelvin. That's because Kelvin is the absolute temperature scale, Celsius can go negative, and doubling the degrees in Celsius does not necessarily mean double the energy. So we're always going to have to use Kelvin. To convert from Kelvin, you just take the degrees Celsius and you add 273. Okay, so just add 273 and you will get the temperatures in Kelvin. Okay, I want you guys to go ahead and try that one for me. Okay, hopefully you tried it. I'm going to go over it real quick. So, first, converting the temperatures. This one becomes, I don't have to plug in my calculator for this, 288 Kelvin and 311 Kelvin. So now I can plug it into the equation. V1, or just going to move it over. Okay, V1 is 2.58 liters over T1, 288 Kelvin, equals V2, that's what I'm trying to find, over 311 Kelvin. So to solve for V2, I'm going to multiply both sides by 311. So times 311 Kelvin times 311 Kelvin. It cancels out there. The Kelvin unit cancels out with the Kelvin units, which leaves us with liters. Cool, that's what we were looking for. Now we have 311 times 2.58 divided by 288, and I got 2.786, so I'm going to say 2.79. Okay, 2.79 liters. That is not enough. Liters. Okay, my board's not working right there. Who knows why? Okay. Come on. 2.79 liters. Okay, and that makes sense. The temperature went up, so we expect the volume to go up. The temperature only went up by a little bit, so we expect the volume just to go up by a little bit. Okay, cool? Okay, cool. Because I did a lot of demos in that video, it went a little long, so I'm going to go ahead and stop this set of notes there, and we'll continue on page 3 in the next video.